Here's where we really start getting into quantum physics, blackbody radiation and the photoelectric effect. All objects emit electromagnetic radiation which depends on their temperature. This is thermal radiation. A blackbody is defined as an object that absorbs all electromagnetic radiation that falls on it. Because no light is reflected or transmitted, the object appears black when it is cold. However, when these blackbodies are heated, they emit a temperature-dependent spectrum termed blackbody radiation. Here's what is meant by a temperature-dependent spectrum. At normal temperatures, we're not even aware of this radiation. For example, people emit infrared radiation all the time, and that's one of the bases of night goggles, where you can see folks at night based on their infrared radiation. However, as objects get hotter, the infrared radiation gets hotter and we feel heat. At even hotter temperatures, objects will start glowing red, and now we're talking more about metals or crystals. Humans don't do that. And at still hotter temperatures, objects will glow white hot, such as the filament in a light bulb. So, as the temperature increases, the color changes, the color of the light, and that's the meaning of temperature-dependent spectrum. Wilhelm Wien, through experimental observation, determined the following equation that related the color of the light, or its wavelength, to its temperature. And this is Wien's displacement law, where lambda max, that just means the wavelength of the light that is the largest in intensity, the one you see the best, times the temperature is 0.28978 times 10 to the minus 2 meter Kelvin. The higher the temperature, as T goes up, in order for this equation to still hold, lambda has to go down, so the wavelength decreases. So the object will change color from red, which has the longest wavelength, to orange to blue, which has a shorter wavelength, then finally to all white. That means that all wavelengths are present in high intensity in the visible spectrum. So all wavelengths are showing up, they have a high enough intensity, and they are all in the visible spectrum, so people will see the colors merging together as white. We have three experimental blackbody curves here. We have the wavelength on the x-axis, and then we have the intensity or the brightness of the light. This curve here is an object heated to 3000 Kelvin. This one is 4000 Kelvin. This one is 5000 Kelvin. The area over here is the visible light, the light that we can see. So you can see the hotter the object gets, you can see more of it with our eyes. More of the intensity is in the visible spectrum right here. Down here at 3000 has very little intensity in the visible spectrum, so we probably won't see it. The longer wavelengths, this is where your infrared is. So this is all well and good. This was experimentally documented. It was accepted. However, the classical theory, the physics classical theory at the time, said that if you have an object at 5000 K, this is what happens to the intensity. As you get closer to ultraviolet, the intensity of the emitted radiation would go to infinity. And because it was near the ultraviolet spectrum, it was named the ultraviolet catastrophe. Classical physics had no explanation for why this curve over here, the theoretical curve, totally failed to describe what was happening in reality. Here's the true beginning of quantum physics. In 1900, Max Planck was able to explain the blackbody radiation spectrum by introducing the concept of quantized energy. He stated that energy associated with the light given off by these blackbody radiators could not be emitted with just any value. Rather, the energy came in packets, or quanta. That's what quanta is. It's just another name for packet. And it was proportional to the frequency of the light. For example, the energy had to be this constant h times the frequency. E is the energy of the light, h is Planck's constant, and f is the frequency of the light. There's another way to show this wonderful equation. Energy equals hf, but frequency, as we showed earlier in the course, is equal to the speed divided by the wavelength, and since we're talking about light here, the speed is c. So E equals hf, or hc over lambda. Now Planck kept working on his analysis, hoping that he could make h equal to 0, because this was such a radical concept. He wasn't quite sure he was on the right track. Of course he was. And he couldn't succeed in getting rid of h because h happens to be a fundamental constant of the universe, and its value is approximately 6.626 times 10 to the minus 34th joules seconds. That's really very close to 0, but it is not 0. This quantum assumption that Planck came up with was then confirmed by Albert Einstein. Albert Einstein was working on the photoelectric effect, which is what we're going to talk about next, which brought back Newton's concept of light as a particle.